Hello dedicated learner, and this is our third module of Lecture 1. In this module, we will discuss taxonomy of machine learning algorithms. We'll briefly review some of the most popular supervised and unsupervised machine learning algorithms. Over the past half-century, a large number of machine learning algorithms have been introduced. The algorithms that work with labeled data are said to be supervised and are placed in supervised learning category. The algorithms that operate with unlabeled data are unsupervised and placed in a category of unsupervised learning. The third group of algorithms is associated with reinforcement learning. The algorithms within supervised learning group are divided into classification and regression analysis group. The unsupervised algorithms comprise two subcategories: clustering and dimensionality reduction. The most prominent algorithms of each type are shown in the diagram. Some of these algorithms we briefly discuss in this module. In supervised learning, a model is prepared through a training process where it is required to make predictions. These predictions are then corrected until satisfactory result is attained. It is assumed that there is an unknown function y of x evaluated at x1, x2, xn, and the goal is to find y of x from the given data. Some examples of supervised machine learning are linear regression and classification with k-nearest neighbor. Regression algorithms are concerned with modeling the relationship between variables. The prediction quality is assessed by an error measure. We have already encountered two such measures: the sum of square errors and the root mean square error. The most popular regression algorithms are linear, polynomial, and logistic regressions. We have briefly discussed polynomial regression in our previous module. In this example, a polynomial regression analysis is applied to model the relationship between body mass index, or BMI for short, and percentage of body fat. We are predicting percentage of body fat given BMI. Blue dots represent training observations, and the green curve is the prediction. Having obtained the model, we, for example, could predict percentage of body fat for BMI being 34. Classification is the problem of identifying to what categories a new observation belongs to. One of the effective but simple classification algorithms is k-nearest neighbor. This algorithm falls in the instance-based learning category. That means k-nearest neighbor does not require explicit learning. It simply compares new observation with k-similar observation in the training set. Then the new observation is labeled based on the majority voting of k-closest instances. So in this case, this observation would be classified as class blue. Another popular classification algorithm is linear discriminant analysis, or in short LDA. We will leave the details of this algorithm for later. Here we illustrate how LDA solves the famous iris flowers classification problem introduced by famous British-Australian statistician Ronald Fisher. The original dataset comprised three species of iris: setosa, versicolor, and virginica, each with four characteristics: the length and the width of petals and sepals, given in centimeters. For the sake of simplicity, we chose only two characteristics: petal length and petal width. LDA successfully partitions the characteristic space into three subspaces. Note that the decision boundaries are linear, hence the name, linear discriminant analysis. In the previous module, we have seen an example of sentiment analysis. Every class was modeled by a probability function describing the likeliness of a sentence being part of a class with a positive sentiment or a negative sentiment. The probability of the sentence "I love this fun film" was classified as the class with positive sentiment because its conditional probability was higher than the probability conditioned by the class with negative sentiment. In general, Bayesian algorithms operate with probability density functions and infer probabilities of possible outcomes. An outcome with highest probability is chosen as a result of classification. At the core of these algorithms is Bayes' theorem. For simplicity, we state it here in terms of the sentiment analysis problem. P of S given C is the likelihood of event S occurring given that C is true. Or in other words, it is the probability of sentence S occurring in the text of class C. P of C and P of S are independent probabilities. And probability of C given S is the probability of interest that allows us to classify the sentence S. The chart on the left shows probabilities of sentence S occurring in the text with known sentiment class. And the chart on the right demonstrates how the sentence is classified by choosing the class with the highest probability. The charts are connected via Bayes' theorem, so substituting these values into Bayes' formula allows us to determine probability of class given a sentence. And in this example, we see that probability of class with positive sentiment is higher than probability of a class with negative sentence, given the sentence S. Neural networks by far the most well-known class of supervised learning algorithms. In most general terms, a neural network is a network of structurally interconnected computational nodes. Mathematically, neural networks are universal approximators, meaning that a neural network is capable of approximating any function to any precision. Among a multitude of proposed neural network models, the most standard ones are the backpropagation feed-forward neural network used in classification and regression, recurrent neural network used in modeling of dynamic processes, for example speech or stock prices, Boltzmann machines, usually helpful in modeling probability distributions, and convolutional neural networks. Beat all other machine learning algorithms in such tasks as image recognition and image synthesis. In this example, an image of a car is passed as an input to a convolutional neural network. These images show responses of neurons in a few consecutive hidden layers. As it can be seen, every next layer represents more complex entities. For example, in the first layer, we have edges and blobs. In the second layer, we already see parts of a car. And in the third layer, we have representation of different types of cars. Ensemble algorithms composed of multiple Bayes learners that are independently trained and whose predictions are combined to improve the overall prediction. Bayes learners are independent and usually quite simple machine learning algorithms, sometimes called weak learners. As long as each of them is doing better than random, the overall performance of the ensemble will improve. There are a number of strategies to combine predictions of each Bayes learner. In case of regression analysis, one strategy is to simply average out results from each learner. For a classification task, a majority rule is often employed. Ensemble algorithms are divided into two groups: homogeneous ensembles and heterogeneous ensembles. The former one consists of homogeneous learners, and the latter one is of heterogeneous learners. Some popular ensemble algorithms include boosting, random forest, and AdaBoost, which stands for adaptive boosting. As we already know, supervised methods require label data. However, it is often the case that labels are missing. In fact, the amount of data produced worldwide appears to be growing exponentially, hence making manual labeling infeasible. That's where methods of unsupervised learning come to rescue. Unsupervised learning works with data that are not labeled and do not have a known result. A model is prepared by deducing structures present in the input data, with the goal to either reduce data dimensions or to group data based on chosen similarity measure. Cluster analysis or clustering is the task of grouping a set of objects in such a way that objects in the same group, called a cluster, are more similar to each other than to those in other clusters. On the left, we have an unlabeled data set, and on the right, this set has been labeled based on how close data points reside to each other. So we have two clusters in this example. Some examples of clustering algorithms are k-means, expectation maximization, and hierarchical clustering. One of the applications that we introduce here is image segmentation. Data points that represent colors or textures in the neighborhood of each pixel in this left image are grouped into clusters. So similar pixels will end up in the same cluster. Pixels from the same cluster are then colored evenly, as shown in the right picture. That results in the image segmentation. Dimensionality reduction algorithms seek and exploit the inherent structure in the data in an unsupervised manner in order to summarize or describe data using less information. This is useful in visualization of high-dimensional data. This also allows to simplify data, which then can be used in supervised learning methods. Some examples of dimensionality reduction algorithms are principal component analysis, linear discriminant analysis, and neural networks. In the figure on the left, we have an example of two-dimensional data that is distributed along one-dimensional curve. Hence, we need one coordinate to describe the position of each data point with respect to this curve. The goal of the algorithm is to determine this curve, or in general, a multidimensional manifold that comprise the data and, in loosely speaking, describe data point in local coordinates within this manifold. In the following application, we demonstrate such an example. The data consists of 28 by 28 pixel images. Each image contains one of 10 digits, as shown in this figure. Each image is converted to a 768-dimensional vector with pixels as vector components. Visualizing 768-dimensional space is troublesome, to say the least. However, applying dimensionality reduction algorithms to map the original vectors to two-dimensional space, which is easy to visualize. This then allows us to see an existing structure in the data. The last class of machine learning algorithms that we will review in this module is reinforcement learning. Reinforcement learning is concerned with the problem of finding suitable action to take in a given situation in order to maximize the reward. Training examples are presented in the following form, in the form of a triplet. The first one is input, the second is output, or some output, and the third one is grade of this output. In supervised learning, we also have had inputs and outputs presented to the learning algorithm. The difference here is that in reinforcement learning, we also have a current state that has to be taken into account. Imagine a mobile robot or an agent whose goal is to find the best possible path to reach the exit in a maze. The agent takes a certain action, and depending on the outcome and its current internal state, this action is rewarded or punished. Then the internal state is updated. Say if the robot gets closer to the exit as a result of a previous action, it is rewarded and the action is reinforced. In this module, we review the taxonomy of machine learning models. There are three major categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Keep in mind that tasks are addressed by models, whereas learning problems are solved by learning algorithms that produce these models. Furthermore, machine learning is concerned with using the right features to build the right models that achieve the right tasks. As usual, I encourage you to work through the following problems. Good luck!